Topography describes the three-dimensional shape of the Earth's surface, including elevation, slope, and landform variability. Traditionally, topography obtained from ground-based techniques. They are time-consuming, labor-intensive, weather-dependent, and often impractical over large or inaccessible areas. So, interferometric synthetic aperture radar InSAR has become a powerful method for topographic mapping. InSAR utilizes the phase information of microwave signals, recorded by a synthetic aperture radar sensor mounted on an aircraft or satellite. By observing the same ground area from slightly different sensor positions, InSAR measures the phase difference interference pattern between two complex SAR images. InSAR relies on the physics of electromagnetic waves. When two radar waves observe the same area from slightly different positions, their phases interfere to produce an interferogram. SAR uses a satellite's motion to simulate a very long antenna, allowing high spatial resolution. It collects amplitude, image brightness, and phase image, which is travel distance encoded in radians. There are three common radar bands: WHC-IHR C-band, L-band, and X-band. Sentinel-1 uses C-band and has a revisit time of 6 days for both. Satellites, the data recorded are mainly in interferometric wide IW, providing 250 kilometers of swath width and spatial resolution of 520 meters. It is suitable for moderate penetration and good for terrain mapping. On the other hand, Allospalter uses L-band and has a revisit time of 46 days. It uses fine mode, scanter mode, and polarimetric mode for observations and is effective to penetrate vegetation. X-band has higher resolution but less penetration. Because the wavelengths are long, SAR can penetrate clouds, smoke, haze, and light rain, making it ideal for tropical countries. Step 1. Capture two SAR images of the same area at two different satellite positions. The separation between these positions is hold the baseline beam is perpendicular to. Step 2. Generate an interferogram. The interferogram is created by comparing the phase of image 1 and image 2. The phase difference is calculated by the formula where R is the difference in distance from the satellite to the ground between the two passes. This interferogram displays color fringes, each representing a phase cycle of 2 pi radians. Because phase is measured only between pi and pi, it wraps like a clock. This creates repeating colorful fringes. It reconstructs the real continuous phase by adding or subtracting multiples of 2. After phase unwrapping and isolating the topographic component of the signal, the phase difference can be directly related to height, the key equation used to compute the elevation. InSAR produced dam support hydrology, engineering, land use, planning, and climate modeling. One study showed that correcting atmospheric effects improved dam accuracy from 13.6 meters to 5.7 meters. InSAR can detect movements before and after earthquakes. For example, in 2016 Pedernales earthquake in Ecuador. InSAR and GPS revealed how the fault slipped and helped scientists classify areas at risk. InSAR and advanced methods like SBS InSAR analyze slope movement over time. This is vital for mountainous regions where field access is difficult. Sentinel-1 based InSAR detects sinking caused by groundwater, extraction, mining, or soil compaction. Malaysia's cities show subsidence rates around -0.5 to -0.6 centimeters year, while some areas uplift by up to 4.5 centimeters year. Persistent Scatterer InSAR, or PS InSAR, is designed to overcome the limitations of conventional InSAR, especially decorrelation caused by vegetation or long time intervals. By monitoring these stable targets across dozens or even hundreds of SAR images, PS InSAR can measure ground motion with millimeter accuracy. This makes it extremely useful for urban deformation monitoring, infrastructure assessment, subsidence detection, and long-term geological hazard evaluation. Two satellites capture radar images of the same area at different times. These images are compared to produce an interferogram, shown by the colorful concentric patterns that represent phase differences. By analyzing many such small baseline image pairs, SBS InSAR generates a displacement map, which shows how the ground has moved over time, whether it has uplifted or subsided. Modern InSAR processing increasingly incorporates AI and ML to automate and improve tasks that were previously slow or error-prone. Deep learning models can now automatically remove noise from interferograms, classify coherent and incoherent areas, and accelerate phase unwrapping. InSAR will be the first dual-frequency L-band and S-band radar mission, offering high penetration, high resolution, and global revisit cycles of 6 to 12 days. Its free and open data policy will benefit researchers worldwide and enable near real-time topographic change monitoring. This mission is the successor to TandemX and is designed to produce dynamic, time-varying global elevation models. Using L-band radar, TandemL will detect small changes in forests, ice sheets, and land deformation with very high precision, shifting global topography from a static map to a continuously updated 4D Model 3D time. Temporal gaps. Some satellites revisit area only every 6 to 12 days, making it hard to detect rapid changes. Vegetation penetration issues, even L-band signals struggle in dense tropical forests. Spatial resolution limits. Radar images are often lower resolution than modern optical data. Atmospheric disturbances. Water vapor introduces phase noise. InSAR are used wave physics, radar geometry, and interferometry to map Earth's topography. By analyzing phase differences, it converts radar signals into digital elevation models. It works day or night through clouds and can detect millimeter-level changes. With new processing techniques,